The professor just walked in the door, so class is definitely happening.
Okay, good morning, everyone. Today's lecture will be the last lecture before Thanksgiving. We will have no meeting on Thursday. Today, let's talk about non-convex optimization. Previously, we always assumed the function f or the sum is convex, but now we still want to solve this composite optimization problem, f plus h, but we only assume h is closed convex. For f, we do not make a convex assumption. We just assume f is smooth and differentiable on a compact set omega, which contains domain of h. So for general non-convex optimization, it is intractable. So we cannot hope to find the global minimum nor even the local minimum. But we are only interested in something that's doable, that is a stationary point. We just look for some point whose gradient or subgradient to this function f plus h is close to 0. And also for the function, the non-convex function, we do not work with the general one, but we work with something that is close to a convex one, that is not very far away. So this is about the smoothness assumption on f. So if we say a function is L smooth, then this is, by definition, this is just a gradient. It's L Lipschitz continuous, right? So from here, we can actually derive that a two-sided inequality. So f of y minus its linearization So we can actually have both a lower bound and upper bound for this Bregman divergence, right? So this is what we have seen a long time ago. For this one, you don't need to use any convex assumption. You just need the L smoothness. Okay, and so we are interested in problems. Let's call this L as a lower bound, as a lower curvature. Call this L as an upper curvature. So we are actually interested in some function f such that we are interested in a function f such that its Bregman divergence is upper bounded by this quadratic function with coefficient m over 2 and lower bounded by little m over 2. And we are interested in the case where little m is much smaller than the big M, because when suppose this little m, both little m and big M, they are positive. But if little m is if it's just 0, then it's saying that this function is convex, right? Or if it's negative, then the function f is m strongly convex. That's not the interesting case. We're interested in where this is positive, so that you have a negative curvature, right? And so from here, we see that if little m and big M, they are both L, then this inequality is automatically satisfied due to this smoothness assumption, right? So we are interested in the case when both of them are smaller than or equal to L. And actually, we're interested in the case where little m is much smaller than the big M. So the function is just a little bit non-convex, but not too much non-convex. Okay. Actually, the M and the capital M and the capital L, they should be the same, because this inequality holds this side holds for both directions. They're equivalent. This has been shown in the probably first lemma in lecture 3 for gradient method. We have shown 5 equivalent statements for L smoothness. This is the right-hand side is one of them. So this one implies this as well. But we don't have the left-hand side. Okay, so that's the setup for the function f that we're interested in. And let's make the notion of different point more precise. So a different point of this minimization problem is defined as follow. So the point x should satisfy 0 belongs to, right? If a point x satisfies this condition, then it's a 0 point. It's just saying that the gradient or subgradient is 0. And we define approximate higher. Okay, so we call higher x and v. Here x is a point in domain of H, v is just some arbitrary vector in Rn. We call this pair to be a row approximate different pair of this minimization problem. Here rho is a positive number scalar. It's just a tolerance here. So as long as the pair satisfy these two conditions, first v belongs to the gradient of f at point x plus domain of subdifferential of h at point x, and also the norm of v, the size of v is upper bounded by rho. So here we are just relaxing this condition a little bit, right? Here we say that 0 must belongs to this subdifferential set, but here we allow some error. V is the error, and we just control the size of the error to be normal than some given tolerance. Right? That's the solution we are looking for. So we are going to develop some algorithm and show that this is going to be one of the notion of stationarity here. So the first algorithm we are going to develop is going to find such a pair and give you the convergence rate and also complexity. That's our first goal here. So the natural idea is just to use the gradient type method, and we just extend the analysis, but don't change the algorithm, and see how it applies in the non-convex setting. In this, okay. So here, this specific problem is called weakly convex because, right? Suppose m is negative, then this is strongly convex. So this is the opposite case when m is positive, so it's called weakly convex. Actually, here m is equal to L, but to see, so in the analysis, just to see where m plays a role, where L plays a role, we will still use two notation, but actually they are the same. So the algorithm is basically the same as the proximal gradient algorithm we have seen before. Step 1 is the one really computes the iterates. Step 2 is just for termination. But here we just compute this this quantity, this vector vk. It's just an iterate for this v notion here, right? And we just check whether this one is less than or equal to rho. If it's true, then we find such a pair. Then xk plus 1 and vk will be this pair, and we terminate. Otherwise, we will stay in the loop. So step 2 doesn't affect the computation. It's just a termination criteria. And the nice thing about this algorithm compared with the proximal gradient method for the convex case is that here we have a specific termination that you can really compute, you can check. But in the convex case, because we are our convergence is in terms of a function value, right? It's the about primal gap f of xk minus f star. Because you do not know f star, so you can never evaluate that gap. It's small or not, right? You can only give a theoretical guarantee, but in the algorithm, just keep running. You do not stop. But here, the difference is that we also have a termination. We also have a convergence rate. But what's more is in the algorithm, you have this checkable condition here. You can compute some quantity and check if it's true, right? Because this vk is actually computable. It's not like f of xk minus f star that is not computable. But this is a nice thing about the algorithm. Just like in the convex case, we also mentioned that I think that's the last question in problem set 1 to give a convergence rate on the size of the gradient, right? This is similar to that one because in that question, you actually develop a theory for some checkable condition, and here it's the same thing. It's different from the function value. Yes.
Is there any criterion for setting that rho? For example, I want to have a notion about how do we set that rho and say that, for example, vk plus 1 is less than that. Okay, we are reached.
This is just the user's choice. If the user want a better solution, then they may choose a smaller rho to tighten up this error. But otherwise, you can choose arbitrary rho. Just like the epsilon for function value determination.
I just have a question about the notion of weakly convex. So is that defined in absolute terms? So like, is there a lower bound for m, or sorry, an upper bound for little m, for how large it can be and still be weakly convex, or is it defined in relation to
because
big M?
if this is larger than L, then this is not because here you want this M to be as large as possible to make this inequality tight, right? If this is actually large, then you want this M to be small, right? You want this because M is positive. You want M to be small. If M is actually large, then it doesn't give you any information, right? Anything larger than this L does not give you more information because this is always true. So you want something smaller than L. So upper bound would be this L.
Okay, so anything smaller than L would be considered weakly convex.
Yes.
Okay.
Yep. Anything larger than L is on this side, right? It doesn't give you more information.
Right.
So you want some tight inequality. So you need this M to be smaller than L.
Okay. Yeah. So the little m much less than big M. That's not necessarily that's just what we're interested in, but it isn't a condition of being weakly convex.
M larger than L?
No, the little m much less than big M. That's not a condition of weakly convex.
That's not. Yeah.
Okay.
That's just some case of our interest in.
Okay. Just want to make sure.
So when this M is small, it is close to a convex function, and in that case, you do not need much effort to convexify the function. So a nice thing about the weakly convex function is that you can convexify it. Let's consider this function. Okay, so usually we say this function is M weakly convex. So M is really the modulus for the weak convexity, just like the mu for strongly convex. And when F is M weakly convex, and also lambda is less than or equal to 1 over m. In this case, this is a convex function. Right, because we can call this function as g and check this condition gy minus g right, because we can do this computation. So the Proximal divergence for this function is the Proximal divergence for this function plus this function, right? And this is Proximal divergence for f. It's lower bounded by minus m over 2 times quadratic. For the quadratic function, the Proximal divergence is just itself, right? And then because this m is small enough, so this is a positive number, right? Negative. So this is greater than or equal to 0, so that we can show that g is a convex function by adding a quadratic, a small enough lambda. Right, so this is why weakly convex function is interesting, because we can add a quadratic to convexify it. So if you want to solve this problem, which is a proximal, if you want to minimize this function, which is a proximal subproblem, right? You can, because now it's convex, you can apply your favorite convex optimization algorithm on it. Right? That's the benefit. And actually, based on this idea, we can develop an inside proximal point framework for it, for weakly convex function. But before that, let's first do this gradient method. Here, because we linearize the function, so in this subproblem, there's no non-convex function, right? This is linear in U, and this is also convex in U. This is convex in U. So the whole function here is approximation plus quadratic. This function is always 1 over lambda surrounding convex. This is the same algorithm as we have applied on the convex function, but the analysis will be a little bit different because our target now is to minimize this value, right? This error, not the function value gap. The first element we have is about the V. So this V and X and V, this is a stationary. So V and X, they satisfy this inclusion here, and also V satisfies this inequality. This is some basic observation on V. So it follows from the automatic condition to this subproblem. We have this inclusion and rearranging the terms, putting this to the left, and add and subtract the gradient of. So just rearranging terms, put this to the left, and we add this to both sides. We add this gradient difference, and add this to both sides, and put this difference, this ratio to the left. Then we recover this this inclusion by this definition. Right, put this to the left. You have the first portion of V, and now you add this one to both right and left. Right, on the left you have this V, on the right this gradient fxk cancels, and this one left, and so you can show this inclusion, right? This is easy to check. And the other one is also easy, just by the definition. Take the norm of V, the triangle inequality, you have this norm plus this norm, and the second one, we use the L smoothness. So now you can upper bound this V by the point difference, right? So from this one, from this lemma, we see that this prior xk plus 1, the bk plus 1, they satisfy the first condition in this row approximate supreme prior, right? You just need to check whether this is small, this b is small enough, right? That is what this step 2 is checking. And as long as you can control the right hand side to be small enough, then b is small. So the goal in the rest of the analysis is to control this difference, xk plus 1 minus xk. Because this is always satisfied. What we need to check is just this one. So this is pretty much like what we do in the in many examples of the IPP framework. The inclusion, which is coming from the automatic condition, is always satisfied. What you need to check is just the inequality in the framework. That is what your algorithm is doing.
Excuse me. Would you please explain one more time why is that always satisfied?
Coming from this one to some algebra, as I mentioned, put this to the left and add this one to both left and right, because this is always true from here, and the algebra is always true. So this is always true for any k, and here is this is always true. But to make this v to be small, you need to control the right hand side to be less than or equal to rho, right?
Yeah.
That's something you need more iterations to do so. But this one, at the beginning, even the very first iteration satisfies this.
Oh, yes.
Here we need two conditions. So we first need lambda to be smaller than 2 over m. And second, we need the function phi to be lower bounded from below by some phi star. Okay, so this inequality, the first one, comes from the subproblem here, right? Because this function is 1 over lambda strongly convex, so we can apply the lemma we always use, right, to subtract. We have more space to subtract a quadratic term on the left, right? This is the lemma we always use, right? Usually we put this to the right, we add a quadratic, but now we move it to the left. And from here to here, we are using the upper curvature of the function. But we are using that m, which is also L. We are using the smoothness condition of the right-hand side of the inequality, right? This linearization plus this quadratic is upper bounding f of xk plus 1. Okay, and now let's take this u to be xk. If we take u to be xk, this becomes f of xk, this is h of xk, so the sum is phi of xk. Right, and this one goes away. This is xk minus xk plus 1, which is the same as this one. So we get
Excuse me, I didn't understand the first line.
this is your objective function in the subproblem, right?
Yeah.
And this is the optimum value of that one. Right? Because this is xk plus 1.
Yes.
And we have some room to add another quadratic, which is this one. I just put it on the other side. Right? And here, take u to be xk, many things simplifies, and we're running term, we have this inequality here. And this is summable, right? You can have a telescope sum on the left. So now, let's just sum them up. Here we need a condition that lambda is small, lambda is less than 2 over m, so that this difference is still positive, right? So that this inequality is making sense. Here we just sum up that inequality for one iteration. And so here we have 5xk minus 5x0 minus 5xk, because this is always bounded below from phi star. So we can upper bound it by this fixed quantity, right? And here we sum them up, and from here to here we are using, this is greater than or equal to. Here we are using the relationship between this error v and this iterates difference, right? We are just using this inequality. And from here to here, we change the summation to be k times the minimum. This is always true, right? And now, rearranging the terms, you can recover this inequality. Right? And then this minimum, so this is the end of the proof. And then this minimum, this goes to 0 at the rate of 1 over square root of k, right? Because the square is on the order of 1 over k. This is 1 over square root of k. And if we want this one to be no more than epsilon, no more than rho, then the complexity is order 1 over rho square. Okay.
In the last line, you're saying that sum of the vi plus 1 squared is greater than k times minimum of all of them.
Yes. Okay, so this is an example where you just use some developed algorithm for convex optimization to solve a non-convex problem. This is a case of a gradient method. We also learned the Frank-wolfe for solving convex optimization and also for the composite case F plus H. This algorithm can also be used for solving weakly convex or non-convex optimization. I'm not going to repeat the algorithm. This is the same as what we have seen before. But let me remind you some of the definitions and the key lemmas. So everything I'm writing down now, you can find in lecture 8 for the Frank-wolfe in convex optimization. In Frank-wolfe, we are not using the same termination as before. We do not compute that vector v. We do not check whether v is small enough. But we use this notion, the Wolfe gap. If you still remember, we used this Wolfe gap to show convergence in the convex case. Because this Wolfe gap is an upper bound, there's a lemma saying that this Wolfe gap is an upper bound on phi of x minus phi star. So this, in convex case, we are interested in the function value gap, right? And this Wolfe gap is an upper bound on it. So whenever this is small, you can show the function value gap is also small. And the nice thing about this Wolfe gap is that it's also a measure of stationarity here. It is stated in this lemma. So first of all, this is always non-negative because it's an upper bound on function value gap, right? So it's always non-negative. And this is 0 if and only if the point, some point x star here, is a stationary point of the composite optimization problem f plus h. I think last time we skipped this lemma, but let me show you part B. Because for any point x, the Wolfe gap is always non-negative. So if we want to show under some condition, this Wolfe gap is 0, so it boils down to just show the other direction, right? S of x star is less than or equal to 0. And so because this is max of something, if you want max something to be less than or equal to 0, then it's equivalent to say for any y, this quantity, this value here, is no more than 0, right? And now let's plug in this x as x star. Right, this is equivalent to say S of x star is less than or equal to 0 for for any y. Right? And now let's rearrange the term. We get h of y right. This is just algebra here. And what this is saying is that negative gradient f at x star belongs to the subdifferential set of h at this point. Right, this is, by definition, they are the same. So then 0 belongs to right. And hence this point is just the safer point to the constant optimization problem f plus h. So Wolf gap is a measure of decisionarity. And in the rest of the analysis, we just want to show s of some xk's from your algorithm for Frank-wolfe, that s of xk is close to 0, is a small positive number. You still need some technical lemmas from the previous lecture. This is some lemma we have seen before for the Frank-wolfe method. And T here is the combination parameter in Frank-wolfe. In Frank-wolfe, given a point x, we do this step, right? We compute some y based on x. And then we take a combination between this point y and the point x to compute the next iterate x plus. That's the Frank-wolfe method. And this is still the subproblem we need to solve in Frank-wolfe, because here we linearize f. So this is still convex optimization, the subproblem. It's not difficult to solve. This is just what we can do, as what we can do in the convex case. And we also mentioned the 3-step size rules. This is for the TK. These are the three subset rules. The first one is predetermined. It's a fixed subset. It's not fixed. It's decreasing, but we determine before the iterates. Right? And the second one is adaptive. You choose minimum between 1 and this one because this is a continuous combination parameter, so it's always no more than 1. And this is exact line search. Basically here, this row eta k is minimizing the left-hand side, and this beta k is minimizing the right-hand side. That's the intuition, right? And for this one, as we shown before, this can be viewed as ak over ak plus 1 from the acceleration, right? This is a lemma we have seen in problem set 3. In that problem, I wanted you to show, I think it's under the exact line search subsets, but this also holds for the second subset rule, the adaptive one. But it doesn't hold for the first one, the predetermined 2 over k plus 2. So this is a sufficient descent condition on the Frank-wolfe iterates, right? If you go from xk to xk plus 1, then you can guarantee this descent, right? You can always show this is true for the two subset rules. So far everything is known. We have seen everything before, either in the lectures or in the problem sets. So building upon all these technical results, we can have the following convergence result. The theorem is also for the second two subsides, adaptive and exact, because we are using this lemma. And we do not have convergence about the walk gap using the first one. I will show you why this is not doable. For the rest of the three, these two, we can have the following statements. So first, this sequence is always non-increasing, just as what I've seen here, right? This is always non-increasing. And this is the strict inequality holds if the point is xk is not a certain point. And also, as k goes to infinity, s of xk goes to 0. We can say something stronger than the second one. It's more or less like this convergence rate result. Sk, the minimum of this s of xk is upper bounded by one term is going to 0, goes to 0 at the rate of 1 over k, the other goes to 0 at the rate of 1 over square root of k. And also all the limited points of this sequence, they are all different points of the original problem. So this one, this directly comes from this lemma and the fact that s of sk is always non-negative. I said this is always non-negative. So this one is always true. And let's see why the strict inequality is true when x is not certain point. Okay. We erase that lemma because we have shown that s of a point is 0 if and only if x star we have this claim. This is 0 if and only if s star is a certain point. Because now we assume that xk is not a certain point. So this is always s of xk is always greater than 0. Right? And hence here we have a strict inequality. And that's why this is this holds strictly here. Right? So because from A we see that this sequence, this function value sequence, this is non-increasing. And 5xk is always bounded from below by phi star. Right? Because this is non-increasing and bounded from below, so this sequence is convergent. And hence the difference because this is convergent, so this difference also goes to 0 as k goes to infinity, right? And again, using this descent lemma here. So the left-hand side, as k goes to infinity, the left-hand side goes to 0. So this right-hand side also goes to 0. And then both these two terms goes to 0. So that means s of xk has to go to 0 as goes to infinity, right? And let's prove part C, which is the most important one. For part C, we also need to use this key lemma. This is again giving us a tight scope sum, right? So let's just sum them up over iterates. Here we just sum that inequality up, and here we can also upper bound it by phi x 0 minus phi star, right? Because this is always lower bounded by phi star. And here just the summation of the right hand side, and it's upper bounding k over 2 times the minimum over the iterates, right? And we can switch this the two means right here. We can put this mean, actually we can put it inside, right? And also here. So this is k over 2 minimum of two quantities. One quantity is minimum over iterates for the s of xi, and the other is minimum of this quantity, right? There is no problem to put this minimum inside. And then this is one quantity, this is another quantity. So the minimum of them is less than or equal to this upper bound. So each of them has to be no more than this one. Right? Then you have two inequalities. From each inequality, you can derive a bound on sk, the minimum of si, and then in the end, putting the two bounds together, you get this upper bound using max. Okay. This is also just algebra. Just do some computation, you will recover this. This comes from the first bound, right? It's easy to see this from the first one. This is from the second one. Right, because here you have s squared, and to get an upper bound on s, you need to take the square root. So you have the second term there. Let's prove D here. So let's assume x bar we assume this x bar is a limit point of the sequence. And then because this is a limit point, so there must be a subsequence that is converging to this x bar, right? So let's assume that the subsequence to be x kj. This is the subsequence x sub k sub j, x kj that is converging to x bar. So now let's again use this Frank-wolfe. So let's consider the Frank-wolfe at a certain iterate from this subsequence at this xkj. Then by definition, because this Frank-wolfe gap is max over this quantity, right? For any y, so this is greater than or equal to this the whole thing here for any y. And now let's consider the case where j goes to infinity. Because j goes to infinity, this subsequence converges to x bar, right? This is by definition of this subsequence. Because of the continuity of f, so first of all, the left hand side goes to 0 because of b. B here says that if k goes to infinity, s of xk goes to 0, right? So the left hand side goes to 0. For the right hand side, this is here from here to here is because of the continuity of gradient of f. From here to here, this is because the closeness of h. There's a notion that I haven't mentioned. It's called lower semi-continuity. So basically, a function. So function h. Here we assume h is closed, right? H is closed. This means the epigraph of h is closed. It's a closed set, right? So then we say the function is a closed function. If the function is a closed function, then this is equivalent to say that h is lower semi-continuous. By lower semi-continuity, if you take the limit, this is greater than or equal to h of x bar, because that's the definition. So the definition for this one, this is saying that and pictorially this looks like a function some function looks like this. This is called semi-continuity. So by because h is closed, so it's lower semi-continuous, and hence by definition, this is greater than or equal to h of the limit point, h of x bar, right? So this inequality is true for any y, and using the same technique as what we have done before, we just rearrange it. Then you can show that this negative gradient belongs to this subdifferential set, so that x bar is the central point. So this proves part D.
Just to make sure, so x naught in that definition, is that the minimizer of h?
Oh no, it doesn't have to be. Just some. This has nothing to do with minimization. Just some point. This is a point x0. Okay, so this proves everything we want to show ABCD. Next time I will briefly give you the reason why the first step size rule 2 over k plus 2 doesn't work. And then that concludes the lecture on non-convex optimization. And we will talk about stochastic optimization next time. There's one problem in the last problem set about acceleration method. So you can get some hint from the non-accelerated version, the first algorithm we mentioned here, the gradient time method. And use some technique we have done previously for the acceleration scheme. Just combine the two together. you need to check the lecture on relative optimization in relative scale for relative smoothness. In that lecture, we mentioned what H is. It's the reference function.
Yeah. So the definitions are related to relative
Smoothness.
I will use these notation to get.
Are you having trouble? Are you saying you're having trouble getting it on
There's a rule for another.
That's what we always use. This lemma, this inequality is the starting point of any prox algorithm. We always use this.
Add another quadratic function to.
So this greeting to this is just optimality. And you have a room for this one. You have stronger inequality, right? Or it's equivalent to subtract on the left. It's the same thing.
Thank you very much.
Sure.
Yeah, there's a formula at the end of the. But yes, you should be able. Yes, you should be able. The way talks about root velocity as formula, and on the last page, and the terms brought out and actually yourself. Okay.